Welcome to my class. I'm Drew Collop. In today's class, we're going to examine the basics of graphing. Graphing is a very important technique to have when working in the laboratory. Oftentimes, you collect raw data, and honestly, no one wants to see your raw data. When collecting raw data, it must be presented in a graph often to show relationships and to visualize what's going on. We are going to be examining the rectangular coordinate system. This is graphing in two dimensions, x and a y axis. Sometimes this is known as the Cartesian coordinate system. When working only in one dimension, we just require a number line. This is a straight line, and we put our units on here. Remember, it must be to scale. 0, 2, 4. You can see every box here is worth 1. That's very important that it's all the same. If I was to change this up and make that 8, you can see these are now not worth 1. This is not to scale. So when building your scale, make sure it is appropriate. It can be in the positive direction. It can also be in the negative direction. Very important, though, that you put your units to scale. Now when we're dealing with values in two dimensions, we use the Cartesian coordinate system. What we do is we add a second number line. The first number line I showed you was horizontal. What we do is we place another number line, in this case, vertical. The point where they cross, the point of intersection, we call this the origin, and they both cross at 0. Let's examine that now. From this graph, you can see we have a horizontal number line, and we have a vertical number line. Place arrows on the end to indicate that these go off in either direction. Where they cross, the origin is at 0 on the horizontal axis and 0 on the vertical axis. We usually label the axes as well. This is my x-axis. This is my y-axis. When we put data on this graph, we call these points ordered pairs because it is in two dimensions. There must be an x value and a y value. Again, this is called an ordered pair. The first number represents the distance on the horizontal axis, or the x-axis. The second number represents the vertical distance, or the y-coordinate. And it's always written in this form, the x-coordinate first, and then the y-coordinate. This is an ordered pair. They're grouped together. The x and the y come together to form one point. And they're always written x first and then y. If you want to assign a letter to that coordinate, you can place that as a capital letter in front. As an example here, I can say this is the point P, and it's at 3, 2. What this means is that my x-coordinate is 3, and my y-coordinate is 2. Let's plot this on the graph. So our x-coordinate was 3, so we start at the origin, and we move 3, we're moving in the positive direction, 3 to the right. 1, 2, 3. So if it was just x, it would be there. But we also have a y-coordinate. Y is equal to 2. So I have to move up 1, 2 points. So I put this here, and this is my coordinate 3, 2. Notice we have 4 different regions on this graph. We have quadrant 1, sometimes known as Q1, quadrant 2, Q2, quadrant 3, Q3, and quadrant 4, Q4. Some things you can say about these quadrants is that your x value and your y value will both be positive. In quadrant number 2, your x value will be negative, but your y value will be positive. In quadrant 3, x value is also negative, and y value is negative. Finally, in quadrant 4, your x value will be positive, and your y value will be negative. So just by looking at the signs on your x and your y value, you can quickly determine which quadrant this goes in. Here's a graph. We have the x-axis and the y-axis labeled. We can see our scale on the x and the y-axis. It is the same scale. It doesn't have to be the same scale on x and y. It has to be to scale within the same axis, but not between the different axes. They can be of different scales. We have a number of points, A, B, C, D, E, and F. What I'd like you to try now on your own is I'd like you to write the coordinates for these points. I'd like you to plot these points. I'd like you to identify the quadrant of points G, H, and I. Give this a try now. Let's take this up. So A is located right here. It is at the origin. Therefore, A is going to be 0, 0. B now, where is B? B is up here. If we look down here, this crosses at 5. And we look across here, this crosses at 5. 5, 5. C now. With C, along the x-axis, we're crossing at -7. Along the y-axis, we're crossing at +3. So -7, +3. The x-coordinate comes first, and then the y-coordinate. D now. Where's D? Down here. D, our x-coordinate is -4, and our y-coordinate is -6. -4, -6. We then have our e-coordinate. E-coordinate is located right on the axis. It is at +7. What is the y-coordinate, however? It doesn't go up or down from that axis, so there is no y-coordinate. Well, there is. It's 0. Finally, F. We have an x-coordinate of 4 and a y-coordinate of -6. 4, -6. I'm hoping this is a review for most of you. So we've determined what those coordinates are on the graph. Let's put some new coordinates on there, some new ordered pairs. So we're going to plot G, which is going to be 3 minus 9. So in terms of our x-axis, we start at the origin, we move 3 over, and then we go -9 down. And that is right here. This is point G. Next point is H. 4 on the x-axis and 8 on the y-axis. Notice they're both positive, so this would be in quadrant 1. We move 4 over, and then we move 8 up, right to there. This would be H. Lastly now, we have I, -5.5, -2. So they're both negative, so this would be in quadrant number 3. So first I go -5.5. 1, 2, 3, 4, 5, and then a half. I got to go somewhere between the 5 and the 6, so right here. And then I drop down 2. 1, 2. So you can see this is not directly on a line, so I have to place it to the best of my ability. This is the ordered pair I. Let's identify the quadrant for each one. G is located in Q4. H is up here. It's located in Q1. Lastly, I over here. This is located in Q3. I'm hoping this is a review for most of you. One very important thing to remember is make sure you label your axes. Either label X and Y, or if you're dealing with data, make sure you label it with the appropriate term, and if there's units, include units. Very important in the laboratory. Again, this should be review. We're now going to jump into graphing of equations. In the previous lecture, we talked about solving equations. Now we're going to graph those equations. Again, an equation is when you have two expressions and they're equal to each other. In this case, if I knew what x was, I could solve for y. Usually in the lab or in science, we're relating one phenomenon to a different phenomenon that we expect is connected together somehow. The x value is often referred to as your independent variable. These are numbers that you are choosing. They're selected by the user, and they're plotted on the horizontal axis. The y values are oftentimes referred to as the dependent variables. These are determined by your selected x values. This would be the data you collect. This is plotted on your vertical axis. So this is your selected intervals that you're choosing to examine, and this is the data from the intervals. What you're changing is the independent variable. It's independent of the experiment because you're choosing it. It goes on the x-axis or the horizontal axis. The dependent variable depends on what you choose. It depends on the experiment. We select an x value, we measure a y value. These are plotted on your y-axis or your vertical axis. Let's plot this equation here. Y equals 2x minus 1. Here we have our x value. This is our independent variable. And here we have our y value. We'll call this the dependent variable. Let's draw an axis on here. Putting arrows at the end. There's our vertical axis. Before we do anything else, I'm going to label x and y axes. So again, this will be your independent variable. And this axis here will represent your dependent variable. Let's put our scale on here. I'll make every 2 boxes on the x-axis worth 1. Over here we go negative. Now we'll label our vertical axis. We'll keep the same scale as the horizontal axis. Every 2 boxes being worth 1 unit. Now the equation we had, y is equal to 2x minus 1. We want to plot this on there. The independent variable is user selected. So let's select something. I'm going to select x is equal to 2. What I then do is I substitute that in here. Y is equal to 2 times 2 minus 1. So you can see I have chosen what x is going to be. I will now solve for y. This is your dependent variable. Y will depend on what you choose for x. So let's solve that now. Y is equal to 2 times 2 is 4 minus 1. Y is equal to 3. So here I'm going to get a data point. X is 2, y is 3. Let's plot that on my graph now. So I'm moving over 2 and up 3, right there. So we had an x and a y value here. We selected the x, and depending on what we selected for x, we solved for y. In the lab, this would be the parameter for measurement. This would be your time you're choosing, the wavelength you're choosing, anything that's going to make up the x-axis. In the lab here, for your dependent variable, this is what is measured. We've only placed one data point on here. The purpose of this was not to talk about graphing an equation, but to identify the independent and the dependent variable. Very important for your work in the laboratory. Now let's actually graph an equation. If we want to graph an equation, what we would like to do is create what's known as a table of values. So I select a number of independent variables, and I solve for the dependent variables. You can see down here, I've asked you to graph this equation, and I've given you the range for my x value, my independent variable. I want you to graph it between -2 and +2. Let's go through the process. Step number 1, sub in your x values and solve for the y values. Step number 2, plot the data points on a properly labeled graph with an x and a y axis. Step number 3, connect the points with a smooth curve. Smooth curve. If it's a straight line, you can use a ruler. If it's not a straight line, don't use a ruler. We don't want jagged edges on our line. We want a nice smooth curve. Very important for the laboratory. Let's graph that now. So let's make a table. We have x values and we have our y values. We're going to start at +2. We're going to go down to -2. Now there's an infinite number of x values you could choose. You could choose 2, 1.9, 1.8, so on and so forth. There's no need to do that. Let's just choose the whole numbers from 2 to -2. So those are our selected values. These are our independent variables. These are our dependent variables. Whatever I selected for x will determine what y is equal to. So we have y is equal to 2x minus 1. So y is 2x minus 1. So what I'm going to do is I'm going to substitute in my x value into each of these 2, 1, 0, minus 1, 2. We will solve it now. 2 times 2 is 4, minus 1 is 3. 2 times 1 is 2, minus 1 is 1. 2 times 0 is 0, minus 1, negative 1. 2 times negative 1 is negative 2, minus 1 is minus 3. We have 2 times negative 2, it's going to be negative 4, minus 1, which is going to be equal to negative 5. So here we have a set of ordered pairs. We have 2, 3, 1, 1, 0, minus 1, minus 1, minus 3, and 2, negative 5. We have 5 ordered pairs. Let's now create a graph. Let's put our axes on here. Label this y, label this x. Let's put our scale on here. This is a very important step, actually. Before you put your scale on, make sure you can have all your data points on there. And you want to try and fill as much of the graph as possible. If we look at our x values here, we have 2, 1, 0, minus 1, and 2. So let's put our scale on here based on that. We'll do 1 and 2. We'll do minus 1, minus 2. Every 3 boxes is worth 1 unit on my x-axis. Let's now examine my y values. I have 3, 1, minus 1, minus 3, minus 5. So I have to go up to positive 3 and down to minus 5. On this axis, I'm going to make the scale different. I'm going to make every box here worth 1, 2, 4, 6, minus 2, minus 4, minus 6. You can see here the individual axes are to scale. On my x-axis, every 3 boxes is worth 1. And on my y-axis, it's also to scale. But in this case, every 1 box now is worth 1. That is completely fine. You can have 2 different scales on your x and your y-axis. The important point here is that it must be the same scale on the same axis. Let's now plot the set of ordered pairs. 2, 3. We go over 2. We go up 3. There's your first data point. We have 1, 1. Over 1 and up 1. Next up, we have 0, minus 1. We do not move from the origin on the x-axis, but we move down 1 on the y-axis. Our next ordered pair, minus 1, minus 3, minus 1, minus 3. And lastly, we have minus 2, minus 5. So we go over minus 2, down to minus 5, right here. Look at the data points now. What shape is this making? Do I need to make a smooth curve? Well, I can, but that smooth curve I can make with a ruler. Why? Because this is a straight line. So connect the points as best you can and put arrows on either side to indicate this goes off in either direction. Here we obtained a straight line. If it's a straight line, it is fine to use a ruler with. One thing to note, y equals 2x minus 1. Here's a little trick for you. What you do is you look at your x variable. You look at the exponent on that. You don't see an exponent, so you know it's a 1. If your exponent is 1, then this is going to be a straight line. That's only if you have one x. If you have x to the 1 plus x squared, that's going to change things up. If you only have a single x value and it's first degree, that means it has an exponent of 1. This means you're going to have a straight line. Technically, you don't need all 5 points then. You just need 2 points. You would connect those 2 points together. I'd like you to try example 2 on your own. Look at this now. Is this going to be a straight line? It will not be. To get you started, make a table of values between -1 and +5. Let me start you off. 5, 4, 3, 2, 1, 0, -1. Your y values, this will be x squared minus 4x minus 3, because that's what y is equal to. Substitute in what x is equal to, solve for y, get your set of ordered pairs. Create the proper axes on your graph, plot your set of ordered pairs, your data points, and then connect those data points with a nice smooth curve. Try that now. Let's take it up. To save time, I'm just going to write this down. I'm going to eventually substitute in my x value, so you can see I'm writing that equation, except I'm removing the x and putting in brackets. Try and save some time. Let's substitute in our x values. And now we'll solve for y. 5 squared is 25. Minus 4 times 5, that's 20. 25 minus 20 is 5. Minus 3 is going to be +2. 4 squared is 16. Minus 4 times 4, which is also 16. 16 minus 16 is 0. Minus 3 is -3. 3 squared is 9. Minus 4 times 3 is 12. 9 minus 12 is -3. -3, -3, -6. 2 squared is 4. Minus 4 times 2, which is 8. 4 minus 8 is -4. -3, -7. 1 squared is 1. Minus 4 times 1, which is 4. 1 minus 4 is -3. -3 minus 3, -6. Notice it was going down initially, and now it appears to be coming back up again. 0 squared minus 4 times 0, that's just all going to be 0. So this one's going to be -3. Minus 1 squared, minus 1 times -1 is +1. Minus 4 times -1 is +4. 1 plus 4 is 5. Minus 3 is going to be 2. So here we now get a set of ordered pairs. I'm going to write them over here because I ran out of space. 5, 2, 4 minus 3, 3 minus 6, 2 minus 7, 1 minus 6, 0 minus 3, and lastly, -1 and 2. Again, we've written it in this format. This first number represents the x's, and the second number represents the y's. Let's now place our scale on here. Notice here our x-axis goes from -1 to 5, and our y-axis goes from 2 down to -7. So I need to make extra space in quadrant number 4. So I'm not going to put the axes right in the middle of the graph. I'm going to write my axes off to the side of it. Label that y, label that x. Let's put our scale on here. Make every 2 boxes equal to 1. That'll fit everything. And my y-axis here, I need to go down to -7. So here I'm going to make the scale slightly different. Every 1 box in this case will be worth 1. So this becomes 2, -2, -4, -6, -8, -10. Let's now plot the data on here now. 5, 2. 5 on the x-axis, 2 on the y-axis, right there. Next up, we have the data point 4 minus 3. 4 on your x-axis, minus 3 on your y-axis. It's going down. We have 3 and minus 6. 3 minus 6 right there, still going down. Once you have the third point, you can start to see this is not going to be a straight line. Why? You can see it's starting to curve a bit. Next up, we have 2 minus 7. 2 and minus 7 is down here, definitely curving off. We have 1 minus 6. Interesting here, you can see it's starting to go up now. 0 minus 3. And then minus 1 and 2. Let me show you what not to do. Don't do this. Please don't do that. Connect it with a nice smooth curve. Best you can. This goes off, and this goes off. This is not a straight line. This is a parabola. Some things to point out here. This bottom value here, this is called your vertex. No values will drop below that point. When you have a second degree term, this represents not a straight line. In this case, it is a parabola. If it was negative x squared, you would just flip the parabola upside down. Instead of looking like a bowl, it would look like a hill. Let's go through example 3 together. So here we have something even more different here. Y equals 1/2 x cubed plus x squared minus 1. And I want you to graph it between the values of minus 2 and 2. Let's work through it together. X, we have 2, 1, 0, minus 1, and we have 2. Our y value here, this will be 1/2 x cubed plus x squared minus 1. Let's sub in our values here now. 1/2 x cubed plus x squared minus 1. Substitute in here now my 2 here and here. And in the end, when I solve for it, I get 2 cubed, 2, 4, 8, times 1/2. 8 times 1/2 is 4, plus 2 squared, 4. 4 plus 4 is 8, minus 1. This is going to be 7. Let's work these out as well. Substitute in 1, 0, minus 1, and 2. And we will solve. 1 cubed is just 1 times 1/2, which is going to be 1/2. 1 squared is 1. So this is 1.5 minus 1. 1.5 minus 1 is going to be 1/2. You can also write that as 0.5. Zeros here. Make that minus 1. Minus 1 cubed. Minus 1 times minus 1 is positive 1. Times minus 1 is going to be negative 1. That's going to be negative 1/2. Plus minus 1 squared is going to be positive 1. Negative 1/2 plus 1 is going to be positive 1/2. Then we subtract 1. Here we have minus 1/2. Finally, we have 2 cubed. It's not 2, it's minus 2. We will cube the minus 2. Minus 2 times minus 2 is positive 4. Times minus 2 is negative 8. Negative 8 times 1/2 is negative 4. Minus 2 squared is going to be 4. Negative 4 plus positive 4 is going to be 0. Our final answer here is just going to be minus 1. So we get a set of ordered pairs. That is going to be 2, 7, 1, 1/2, 0, minus 1, minus 1, minus 1/2, and 2, minus 1. So let's plot this now. You can see here I have to go up to 7 and down to minus 1/2, or minus 1 actually. So let's draw our horizontal axis further down to accommodate that 7 up top. And we'll draw this one right in the middle. Y-axis, x-axis. Let's put our scale on for our independent variables. These are the ones we selected here. Independent variables. Let's do -1 and -2, 1 and 2. So every 3 boxes will be worth 1 unit on my x-axis. For my vertical axis, my y-axis, we'll have to make the scale different. Let's make every box worth 1. So every 2, I write a unit of 2. And we'll go negative down here. Let's plot these ordered pairs now. 2 on the x-axis, 7 on the y-axis. Right there. 1 on your x-axis, 1/2. That's going to be halfway between 1 and 0. We have 0 and -1 right here. -1 and -1/2. It's going to be right here. And then lastly, we have 2 and -1. Again, I missed that negative again. -2. Always double check your work. Here we have -2 and -1. -2 and -1 is going to be right there. Let's now connect it with a nice smooth curve. What is this one going to look like? It's definitely not a straight line. It was looking like a parabola until I got to -2. You can see here, we have a 3 there. This is going to be a cubic function. What does a cubic function look like? It looks like this. It has this characteristic pattern to it, something like that. So by looking at the exponent on your x variable, your independent variable, you can oftentimes determine what that graph will look like, whether it will be a straight line, a linear equation, whether it will be a parabola, x squared, or a cubic function, x cubed. In this course, we will mostly be working with linear equations, straight lines. Let's now review the rules of graphing. This might be helpful to print this page off from your notes and keep this when you're making graphs for your laboratory. To be honest with you, no one ever wants to see your raw data unless they think you've made a mistake. People don't want to see that. They want to see your data as a proper graph. They can quickly visualize relationships in a short period of time. This requires neat and clarity of your display. So these are rules so you can make sure you communicate your information clearly and neatly to your audience. Step number 1, the title. It should be a precise title at the top of the page. Underline the title. In the laboratory, they want the date in the top right corner. Please don't call it a graph. It is called a figure. Figure 1, figure 2, figure 3. In the lab as well, sometimes the instructor wants your name, your course number, and your section in the top right as well. The biggest thing here, though, in your title, never use the word versus in your title. If I had a graph that was like this, and it showed some sort of relationship here, let's show you some data here. This would be a growth curve for cells. We have time along the horizontal axis. I've selected the times and I've counted the number of cells. So my dependent variable is the number of cells. Again, this is my independent variable. Why? Because I chose the times. This is my dependent variable. Why? Because it depends on what time I choose what the cell numbers are. When you're writing a title for this, don't write this cells versus time. As an instructor, I hate that. Why do I hate that? Because it doesn't bring anything extra to this graph. I can see it's cells versus time if I just look at the axes. So writing cells versus time doesn't tell me anything extra. So don't use versus ever in your title. A more appropriate title might be describing what the cell line is, what was used to count the cells, what days it was used. So I could say something like, these are BHK mammalian cells counted using a Coulter counter during a 240-hour period. You see, that title is much better. It doesn't just repeat what's in the axes. It tells me more. So remember that. Don't use the word versus in a title. For your axes, the independent variable should be on the x-axis and your dependent variable should be on the y-axis. If there's any units of measurement, include that in as well. Like right here. Time was in hours. This time could be in seconds, it could be in days, it could be in years. So very important, you put your units in place. What about scales? You want to choose a scale that gives you a range of values to use maximum space on the graph. As a usual rule of thumb, minimum 75% of the graph should be showing your line. To do this, find the range. To determine the range, we take the maximum value, we subtract the minimum value. This is your range. We then divide this range by the number of squares you have and round up. This would be a good way to maximize the amount of space you use in your graph. Make sure your graph is to scale within the axes. However, your x and your y-axis don't have to be in the same scale. The origin does not have to be on the graph itself. If you don't have a 0, 0 point, there's no point in putting it on there. Again, make sure you label your axes with the appropriate scale. One of the biggest mistakes students make is they change the scale somewhere along the line. When you put your data on the graph, you plot it as a single point. If you'd like to, you can surround the point with a small circle if it's hard to see. Lastly now, connect the points with a smooth curve or draw a line of best fit for your curve. As an example, here is a graph I get, and let's put the data on there. Don't do this. That's inappropriate. Why? When you're collecting data in the real world, it's never going to be exact. There's going to be some small deviations here and there. So what would be better is if you draw a line of best fit. Imagine you're taking an average of all the points, something like that. Now notice, it doesn't touch most of the data points. That is completely fine. This is the line of best fit. It shows the relationship of my x-axis compared to my y-axis. That's what we're looking for. Is it a straight line? Is it a curve? Does it curve up? Does it go down? We can look at the graph and make determinations without reading anything else about your report. All these rules being stated, make sure you clarify what your instructor or your supervisor would like. Sometimes there's some small deviations from this. So we'll maybe call them guidelines more than rules. This is a good set of guidelines to build the best graphs you possibly can. So in today's lecture, we introduced the idea behind basic graphing. Your x and your y-axis represents your independent and your dependent variables. What you're choosing goes along the horizontal axis. What you're measuring goes along the vertical axis. We then reviewed plotting linear equations, straight lines, second degree equations. This would be x to the exponent 2, making curves or parabolas. And finally, cubic functions. This is when you have x to the exponent 3. We did all this using a table of values to determine a set of ordered pairs. Moving forward, there's actually easier ways to graph this, and I will teach you some of those in future lectures. Finally, we examined the guidelines or rules when making a graph. Making a graph is something you're going to do all the time in the laboratory. Very important skill to have. Again, I would advise you print off this last page and you keep this with your chemistry, your biology, whatever labs you're working in, and you follow these to try and build the best graphs you possibly can. That's all for today. Until next time.